In section 1.2, we're going to be looking at matter. So we're going to talk about what matter is and the characteristics of matter and different measurements that we can take by looking at objects. So matter is anything that has mass and takes up space. So mass is the amount of matter, the amount of stuff in the matter, and space is a reference to volume. It's a reference to the amount of space that the object will take up. So there's lots of different types of matter, and these are all examples of matter. So in this image, you see lots of different things. You see water and lava and gold bars, and you see air that's moving, wind through the trees. You see vapor. So all these things are matter. Matter is all around us, and matter can take different forms, and matter can also change forms. So all of these items in the images, these are all different examples of matter and things that are in different states of matter. Some of them are solid, some are liquid, and some are gases. When we look at mass, we're going to be trying to determine the amount of matter that is in an object. And the way that we do that is by measuring it by using either a digital scale or by using a triple beam balance. Now, a triple beam balance is something that you may have used even in middle school. And what you do is you take the object that you're trying to determine the mass of, and you put it on this pan. And then this is called a triple beam balance because it has 3 beams. So you'll move these counterweights on the beams, and you move them a small amount at a time in order to get this pointer to match up at this 0 mark right here in the center. So once you do that, then that tells you that the amount of mass on the pan is equivalent to the mass of the counterweights on the triple beams. And so that helps you to determine the mass in an object. And usually we're going to be measuring mass in grams. Unless it's something that's larger, then we might measure it in kilograms. There's a fine distinction between mass and weight. And these are something that a lot of people get confused. So we looked at what mass is. So what is weight? Well, weight is going to be looking at the mass of an object, but also looking at the pull of gravity on that object. So when we're looking at the mass of this little astronaut here on the Earth, the mass of this astronaut is 68 kilograms. Its weight is 150 pounds. So the mass is the amount of matter that's in the object, so the amount of matter in this astronaut, but the weight is going to be dependent on the pull of gravity, which on Earth is 9.8 meters per second squared. So if the astronaut travels to the moon, then the mass is going to remain the same because that astronaut still has the same amount of matter, but its weight is going to be different because the pull of gravity on the astronaut is going to be different on the moon, just like it would be different in space. So if a person travels from one planet to another planet, then that person's mass stays the same, but the weight is going to be different on different planets. And that's because it's a reference to the mass dependent on the pull of gravity on that object. When we look at volume, volume is going to be the amount of space that something takes up. And we've looked a little bit at finding volume and determining volume of solids and liquids. So we're primarily going to be using these 2 different procedures throughout the year. So we'll be measuring volume of liquids using graduated cylinders. And the graduated cylinder is usually going to be using milliliters, ml. So when the water in this case is placed into the graduated cylinder, it fills up the graduated cylinder to whatever mark that you fill it up to, and then it's going to form this kind of curved surface. So that curved surface is called the meniscus, and this is kind of a enhanced view of that, so you can see it a little bit zoomed in. So when you're trying to read the meniscus, you make sure that you look at it straight on at eye level, and also that you're reading it from the bottom of the meniscus. So you're reading it from the bottom of the curve, and that will allow you to determine the volume of the liquid. When you're looking at the volume of a solid, like a rectangular prism, you're going to use length times width times height. So there's different equations for determining the volume of a pyramid, for example, or the volume of a cone or cylinder, but we're mainly going to be using length times width times height for determining the volume of rectangular prisms, solids, and also for using the graduated cylinder in order to determine the volume of liquids. Displacement is another method we're going to be using throughout the year, and we have used this in some of our labs. So when we look at determining the volume of an irregular object, we're using the method of displacement. And so what that is you start off with an initial volume of water, so a known volume, which is 50 milliliters in this case. You place the object, like this crystal here, into the water, and it's going to displace. It's going to push out of the way a certain amount of water. And the amount of water that it pushes out of the way, the amount of water that it displaces, is going to be the volume of that object. And so you will have an initial volume, and then you will have an ending volume. And so you're going to take the ending volume minus the initial volume, and that gives you the volume of this object, because once this object was added to the graduated cylinder, it pushed out of the way a certain amount of water in order to account for the volume of that object. We're going to be talking a lot about elements throughout this year. And so when we're talking about elements, we're referring to all the things on the periodic table. So the periodic table is going to have a list of all of the elements. So each box on the periodic table represents one element. So this square here represents the element neon. And when we look at different images of models of elements, you're going to see them represented by just one shape or one color. So for example, this represents an element because it is purple circles, and it's continuously purple circles. There aren't green circles with it. There's no triangles with it. It's just that one thing, that one atom that's repeated throughout that substance. So elements are pure substances. Atoms are going to be the building blocks of matter. Atoms are usually going to be referred to when you're talking about an amount of an element that is present. So an atom is going to be the smallest unit of an element that maintains the properties of that element. So the element gold, as in the gold bar here, is made of gold atoms. So again, usually we are going to be using this word atom when we're referring to the structure, as in the Bohr model here, or when we're referring to the amount of those atoms that are present in a particular compound or in a particular chemical formula. So what is a compound? So when we have a compound is going to be made of two or more different elements. So compounds are not going to be able to be made from the same element. It has to be different elements that are present. Compounds are also pure substances because they're made only of elements that are chemically combined. And compounds can be broken down. However, compounds can only be broken down by chemical reactions, by chemical means that will separate the bonds between those individual atoms. So for example, in carbon dioxide, we have two elements that are present. We have carbon and we have oxygen. But in this specific chemical formula, we have one atom of carbon, but we have two atoms of oxygen. So we have two oxygens that are present, only one carbon that is present. So when you are referring to the amount of the substance that is present when you're looking at an element, then you're going to use the word atom, and that's going to help you to quantify what you have in that particular compound. So what if you have two of the same element bonded together, like this example of hydrogen? So it can't be a compound because it's not two or more different elements. So what does that mean? What is it? So this is going to be classified technically as an element, but it's going to be a diatomic element. It's going to be a diatomic molecule. And the reason why, if you look at your stems, di means two, and atomic refers to atom. So it's two atoms of the same element that are bonded together. So that means that this particular substance, again, is not a compound because it is not different elements bonded together. It's the same element bonded together. So this is a diatomic molecule. So water, if you look at this, H two O, so this is two H's and one O. So we have two hydrogens, one oxygen. Is this diatomic or is it a compound? What's made of two different elements, so that's going to be a compound. If we look at this example of ammonia, NH3, we have nitrogen and we have three atoms of hydrogen. We have NH3. So that is not going to be diatomic. That is going to be a compound because it's made of two or more different elements. C6H12O6, this is glucose. So this is not going to be diatomic. This is going to be a compound. It's made of carbon, it's made of hydrogen, it's made of oxygen. And in order for it to be a compound, it has to be two or more different elements. Same thing with sodium hydroxide, NaOH. It's got sodium, oxygen, and hydrogen. So this is a molecule of sodium hydroxide. It's a compound, two or more different elements. So here are other elements that are going to exist in nature as diatomic molecules. So all of these elements are going to be found naturally paired together with one of its buddies. So chlorine, you're going to find chlorine as Cl2, which means that you have two chlorine atoms bonded together. Iodine, I2, it's going to be an iodine and another iodine atom bonded together. So all of these elements, hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine, those are all naturally found as diatomic molecules. So these are not compounds because they're not made of different elements bonded together. It's the same element that's bonded together. So when we look at the term molecule, molecule is going to be the smallest unit of a compound that retains the properties of that compound. So when we're looking at water, for example, this is just one water molecule. And we said that water is a compound, and that's correct because water is made of two or more different elements. It's made of hydrogen and oxygen. So this is one molecule of water, one molecule of the compound water. And the term molecule is used sometimes to refer to those diatomics that we just looked at on the previous slide. So when you're looking at hydrogen, if you're just referring to the element hydrogen, then you're just referring to one atom of the element hydrogen. But if you're referring to the diatomic element, that diatomic molecule, H2, then that's going to be using the term molecule as a reference to it being diatomically bonded together with its buddy. So if we look at this example, this line right here, so this line is 1 inch, and 1 inch is equivalent to 25.4 millimeters. So we're looking at the length of this one line. So 1 millimeter is equal to 4 million water molecules lined up. Molecules are tiny. Atoms are even tinier than that because the individual atoms make up the molecule. Those individual atoms are bonded together to make up that particular compound, in this case of water. So in 25.4 millimeters, we're going to have 101,600,000 water molecules. So while we have this line right here, this represents 1 inch, that's going to represent the amount of 101,600,000 water molecules. So if you were to just have 1 millimeter, which is super teeny tiny, then that's going to represent 4 million water molecules that are lined up together. So that just hopefully helps you to have a better idea of the scale of molecules and atoms. So think about the ocean. How many water molecules must there be in the ocean?